So drag force diagrams, it's basically the pulling force of the train. In the beginning, theoretically, you should have infinite drag force. Because why? Because we're looking at electric motors. E is torque times omega. In the beginning, at velocity equals 0, since there's rolling, omega is also 0. So the locomotive is stationary, there is no motion at all, which means the wheels are stationary. Theoretically, we should have near infinite torque. Of course, we cannot have that because not only is the motor itself limited by what it can do, there's another bigger limitation, which is the coefficient of friction. That is where you get this limitation. Take this as the track, the wheel, and then it has some normal reaction.
Yeah.
Mu times n, let me take it as mu mg. This is the limiting thing. Mu mg, the radius of the wheel, mu mg times r would be the limiting torque you can make. If you make any torque beyond that, it will still be going to the wheel, but the wheel will slip already. That's useless because it's being wasted and the wheel is getting damaged. So in the beginning, the limitation is given here by mu mg. If you have an incline, then your mg itself is changing because now it is you have an angle theta. It's mu mg cos theta. So now you have even lesser starting drag force. When during the case, then you need more drag force.
Okay, when you say drag force, you're talking about the wind force, right?
So he calls it drag force, but it's basically the tractive effort is the technical term in English. It's the amount of pull the locomotive is giving to other parts of the train in newtons.
Yeah, okay.
That's a force. So here the weight of the train is pulling it back by mg sin theta, but now my drag force is also decreasing. The pulling tractive effort is becoming mu mg cos theta. So if you have a locomotive which is going on a hill, you usually make it with a higher mass. You use like thicker panels or you add ballast weight and so on. So that just because you have a higher drag force to compensate for the incline. So this limitation we will get by using the drag force, by using the coefficient of friction. Let me just open up my slides on that. Yeah. So usually you have the power given to you, kilowatts, maximum speed, that's so that you know where to stop drawing the graph. The weight is given because we need the mu mg term, coefficient of friction. Radius of the wheel is missing here, right? The radius of the wheel definitely matters. This is the question from the class.
Yeah.
And you have the wheel diameter given to you.
Mm.
So let's do more about this example. Vmax is 200 kilometers per hour. How much does that become in meters per second? Multiply 5 by 18. 55.55 meters per second. Pmax 10.4 megawatt. P constant 7.4 megawatt. So this is available from 120 to 200. Maximum drag force is, so here it was made easy for you, the coefficient of friction was not given, instead we directly calculated the drag force. F max 312 kilonewton. So in this diagram we have like three constraints. The first constraint, like I mentioned before, was from the friction, and the next constraint happens because you are keeping the same torque because the force is same. What is torque? Is force times radius. So So that force is coming from this point. So Fr is the torque. If I look at the power graph, power versus velocity, initially it's making zero power because it's not moving, but it's making some torque. Gradually it increases. At some point it reaches the maximum power that it's able to deliver. Let's look at this constant power curve. Let's say you're running it at nominal operation, not overload or not for short time. So long time, you want to stop there because if you make, let's just imagine this part is not there. You cannot make any more power with the motor you have. So at this point, you have no choice but to decrease the torque. The torque comes down automatically because the power is limiting you and it stays like that.
Yeah.
And that's why, because the torque is coming down, it's decreasing. And why is it a curve and not a straight line? Because it's P divided by V. So it's like y equals 1 by x type of stuff, like k by x. Because x here is the velocity, right? This k is your power. So from that point, it's decreasing. Now, then you have another point, which is the maximum power line, which we can also draw with 10.4 megawatts, which is looking at the extreme limit of this locomotive. So you can keep going for a longer time or to a higher velocity with the same torque, because this line is continuing and it goes till there. Now at this point we stop. You see, the drag force starts decreasing at a higher velocity than earlier. So here it starts decreasing at this velocity itself, but here it's at a higher velocity and then it starts decreasing. That's why freight locomotives and passenger locomotives are made so differently, because their demands are different. Passenger train is focusing on speed, the mass is much lower, so this maximum drag force is not the focus to you. That's what is shown here. Look at the IC train, at any speed it needs a lesser force because it weighs lesser, but it's going to go to a higher speed, so that you just change the gear ratio. With the same motor power, you just change the gear ratio for lower torque and a higher top speed. So this graph that we saw here stops at 200 because that's the mentioned limit of this locomotive. But if you had the passenger train, you want to stop at 300, so you start with a lower initial torque, but you go to a longer velocity.
But you're assuming the drag force is the same, right? Because it's the same motor.
Yeah, but that's just in general I'm speaking. But in the question, what we are drawing is the drag force versus velocity. How do you get the drag force? You get the torque based on the velocity, and then you divide the torque by the radius.
Okay, yeah.
So let's say you want the drag force here. Like till that doesn't matter. So you need to do some preliminary work before you start drawing. The first thing, if here we have the force given to us, but if not, you will find the mg cos theta. So let's say it was given as
mg.
mu mg cos, mu mg, and there's no cos theta. So friction would be mu mg. Then the torque would be F times R. Friction force times R. Radius of the wheel is given to you. Then you will find the velocity at which it will start decreasing, this point, because until then it's a straight line. You want to find this point. So you do P by T, that gives you omega. You have to convert that omega to velocity. P equals R omega, you know that.
Yeah.
So I just divide by radius. So P divided by, I have to multiply radius. P times radius of the wheel divided by torque, that will give you velocity. I know what is the limiting torque, I substitute that in, that will give me this velocity. That will give me this point. So till then you know it's a straight line, you don't have to do any extra calculations. Beyond this point, as the velocity increases, the torque is decreasing, now because power is constant. Until then power was not constant, power was increasing like we saw here, but then it's becoming constant. This P I took was the maximum. Let's say we are drawing this line. Forget this. I'm taking the maximum power line. So P max, I will take it as 10.4 megawatts. And in this case, the force is given directly, which is T by R. So what I would do would be this P divided by F. So to get this velocity, let's say that it is 120 here. They already gave you the velocity in the question. But if not, then you would have to find that. Yes.
Do we have to use the torque because power formula is also force into velocity?
Yes, correct. We can do that. Yes.
Yeah.
Torque by radius is also force. So this is basically P divided by F equals V because power is force times velocity. So this calculation was simplified for you. If
To
not,
get these 2 points, we just have to
take the
divide
two different power
powers and
by the tractive force.
drag force.
Drag
Yeah,
force
but
is the
see,
maximum drag force. In this case it was given, but if not, it's just mu mg.
Yeah.
That's all. Then you get those points. Then you take constant power, take higher and higher velocities, then you get more data points on this curve. That's all. Clear?
Yeah, that makes sense. Yeah. But now my question was, what are these like 800 and then what are these gradients? The resistive gradients, the drag resistance.
So that is basically this zero gradient. It means it's on flat terrain. This is also flat, but lower. So that's the limit basically. So here it's having a lower mass, 600 tons, so it can go faster.
Mm-hmm.
Here it's even lower, 400 tons, so it can go even faster. The next one is a 5% gradient. So these two are the same line basically. You can either take 400 tons at 0% gradient or 300 tons at a 5% gradient. What does a 5% gradient mean? It means the slope ascends 5 meters up for every 100 meters you go forward. This is not needed, it's just marked in general. So like I said, your tractive capability decreases on the hill because of what I mentioned there.
Yeah.
The gravity is pulling you back and your normal reaction has gone down, so you have lesser friction. So the whole thing is shifted down.
Okay.
So in the same graph, imagine if you draw a new curve
Mm-hmm.
for the case of this. First of all, you would have mu mg cos
Yeah.
theta, and from that you would have to subtract mg sin theta. So this will be your F max. Then you have a gradient, and that will basically be somewhere lower, like that. Then it will drop similarly. Because the force is lower, it will drop at a higher power, higher velocity.
Yeah, but I don't understand how do you read those drag resistance because they're just lines, right? So
So those are given lines. I think for this much mass, we know it's going to have this much resistance. But that is calculated based on the equation of Southhoff, which is unnecessary for the exam, but he just gave it for
Yeah.
information. So based on this equation, you can calculate how much rolling resistance is created by this much amount of freight carriages. That one has the. So one important thing that you might need to know is how to convert this percentage gradient into an angle, because all our calculations are based on angles.
yeah.
Theta, tan theta is 5 by 100. Theta is tan inverse 5 by 100. Then you have the angle, then you can do whatever you need with sin theta, cos theta.
But I still don't understand how do I read those three lines though? Because
Those three lines, they have been drawn in advance based on this equation,
okay.
and those intersection points tell you where where it's going to stop accelerating, which gives the top speed.
Okay.
That's all. So you
Okay,
draw
okay.
draw the drag
okay.
force line as per your calculations,
Mm-hmm.
and this line you have drawn based on that equation.
Yeah.
And this intersection point gives you the top speed
Okay.
at this
okay.
power, and that top speed is at that power.
I see. Okay. It's like a 3D graph at that point, yeah.
No, it's still 2D there because you just intersection points.
Because
It's not planes.
so the drag resistance has is dependent on drag force and the
No, drag resistance is not dependent on drag force. Drag resistance just tells you for this much load at different speeds how much drag force is needed. It doesn't care what is being
Repeat the
given.
last part.
See, in this graph we're drawing two things. So the maximum drag force on the maximum power
Yeah.
lines,
Yeah.
that's the input side, the locomotive. Output side is the carriages, which have the mass, right? And they have rolling resistance, just like a car does. And on the output side is basically like demand. So if you remember that one question we did in class about centrifuge, it is there.
Probably not.
So this is your supply. This is your supply of drag force, supply of force. the force demand. Just tells you at different velocities for a given mass of freight how much force is needed to keep them at that velocity. Not even to accelerate, just to keep them there. Because the wheels have friction and there's rolling resistance. This intersection point gives you the top speed. Because beyond this point, the force is decreasing, but it needs more force to reach that speed. And to the left of this point, the force applied is higher than the force needed, so it accelerates to a higher speed. Then here it stabilizes, it stays there. But I think the force demand is definitely not, probably not going to be part of the exam, even if you draw a drag force diagram. Your drawing part will be the maximum drag force and the power curves. So the maximum drag force part, force is constant. Maximum, the power curves, power is constant.
Okay, that makes sense. No, the thing is, like, I was trying to see the formula. Okay, you get some answer, right? Whatever. But when you try to match the units of that to the drag resistance curve, they were not matching in my opinion, right?
Units should match.
Because like
drag resistance is also for Newton.
drag resistance is based on that formula, right?
Sort of.
It's basically plug in the formula, you get the values, right?
Yes.
Can you scroll up?
Southhouse equation, you don't have to know that.
No, scroll up. That's the other one. This
On the
formula,
same
right? So what I was thinking is like A is what meter
You
per
see
second.
here the equation is different because it's Newton per ton.
Okay.
So the whole thing, what you get is just amount of newtons needed per ton of mass, and then you multiply mass, and then you will get newtons.
Okay. Okay, makes sense. Okay.
Because you can see here you have Newton, and then you are dividing by mass.
Yeah.
Newton per ton is the unit throw.
Okay, that makes sense.
See, additional,
Just so needed, yeah.
not needed. What is definitely needed, drawing the input side, the supply.
Yeah.
So now you know how to find this force,
yeah,
right?
Yeah.
You know how to find this point where it
Yeah.
starts changing,
Yeah.
and you know where to stop. That is given in the
Yeah.
question because you can't calculate that. So don't make this one common mistake. Let's say the top speed given was 200. Don't have any data points after 200 because it cannot reach there.
Yeah.
Those data points are meaningless. Do not have anything, any data points to the right of the given top speed. I think that's all about drag force diagrams. Similar to the torque versus RPM curves. Different. But I was very surprised to learn that what I mentioned earlier, that to increase the pulling capacity of a train, they increase mass of the locomotive. Because usually we think for efficiency we want to have lighter cars, lighter everything. But here to be able to pull more stuff, you increase the mass of the locomotive itself.
Yeah, I mean, it sounds counterintuitive. Yeah.
Yes. That's why these passenger trains, they don't go for locomotives, which is like a separate engine and then you have cars behind them, but you have motors below each of the cars. So that, because each of the cars has a normal reaction, right? And you don't need to increase their mass because you're using that normal reaction only for that part of the car. And the next normal is for the next part. So you have much higher top speed which you can reach with there. You don't need to additionally increase mass. In those kinds of trains, it's beneficial to decrease mass because the mass that is being, like the F is mu mg, right? Drag force. You know the force demand, as per Southhouse, is going to be some k for that speed multiplied by the m. So you divide them, the masses cancel out. So then it's in your interest to decrease the mass. Sorry, just additional information I'm telling you. That's why the configurations between passenger trains and goods trains are different. That also reaches higher top speed.
Alright, just one final question before we go. There was a thing you were mentioning about step ratio. What was that thing?
Step ratio? It's on
No, the step gear ratio.
Yes, yes.
I understand what you're trying to show on the board to the guy.
So if you have a gearbox, let's say you're running the engine at a constant RPM. It's giving a constant amount of torque. It's a variable speed gearbox. 4 different gear ratios. Which gives T1, T2, T3, T4. do this constant thing, constant step ratio thing, what we are taking is I2 by I1 equals I3 by I2 equals I4 by I3.
Yeah.
Basically, the ratio between one step ratio and the one before it is
Yeah.
kept constant.
Mm-hmm.
And you use that to find out how many gears you need to split your range into, because when you're designing a gearbox, you know your input torque
Mm-hmm.
and you know like how wide a range you need to go between. Let's say for a tractor, you know that it needs to plow the fields at like 5 kilometers per hour, but also pull the trailer at 70 kilometers per hour.
Mm-hmm.
That is your speed range.
Yeah.
And they take the input RPM to be constant because the diesel engine they run at around 1400 RPM. It's kept constant.
Mm-hmm.
And the wheel size is constant.
Yeah.
So the RPMs are changing.
Yeah, makes sense.
And based on the how spread out the RPMs are, you get your step ratio.
But that's the formula, right? Like C is equal to like V over Q1 minus X.
Yeah.
That's the formula, B max.
Yeah. So you know your Vmax
Yeah.
that your car or vehicle is going to
Yeah.
go for. You know the V min it needs to operate at.
Yeah.
And using that, and you know for my constraints how many gears I'm going to split into.
Yeah.
Then you get the C, so that you
Yeah.
know the actual gear ratios, how many teeth to put on each gear. So
Okay.
if it's a 5-speed gearbox, you get a different step ratio. 6-speed gearbox, you get a different step ratio.
Okay, so C is like the ratio of
Between the two
each,
ratios,
yeah.
reduction ratios, exactly. That's called step ratio.
Yeah. Okay. So
So usually it's in like this, where you have the number of gears and
Yeah.
Vmax, Vmin, and you get C.
yeah.
But if they flip it around and they ask the number of gears from Vmax, Vmin, and C, it's
Yeah.
like that. I made this equation.
You just make X the subject, yeah.
Yeah.
Okay, that makes sense. Yeah. I just one final question. Like in his slides, right? He gives like so many parts. Like he gives like cross sections of different parts and like the label. Like, are they important? I don't know. It's like, should I memorize each part name or what?
You should memorize what each part of the hydraulic circuit is for that exercise.
Okay, but that you can tell from the diagram.
Right. But the other parts are fine. You don't have to.
Where like.
I know what you're talking about. Like there's a tractor, there's transmissions, and each part is labeled.
Yeah.
I don't think you need it. You need to know that. What you need to know is like a simple, some kind of cylindrical cross section with a hollow section.
Yeah.
You need to be able to read the inner and outer diameters. That's all.
Okay.
For calculating moment of inertia. Complicated engineering drawings, reading that is not
Yeah.
a part of the exam.
It seems like irrelevant. But he added them, so I was like, what are these?
He likes to give additional information without saying it's additional. So was that clear for you also?
Mm.
Okay, you can do that. It's a similar thing, right? But here you gave in terms of the angle, how much it's changing. Then you draw the new portion based on the angle shift. And then you That's it?
Yeah.
Okay.
Are you gonna do more questions?